Hi everyone, in today's lesson we're going to talk about limits at horizontal asymptotes. When determining limits as x approaches infinity or negative infinity, we're actually asking for a horizontal asymptote and we're actually examining the end behavior of the graph. So when I'm talking about, say, this graph, the limit as x approaches infinity of f of x, I'm asking as x goes to the right, which is positive infinity, where are the y values, f of x, where are they headed? So where's the curve leveling off to? You could see that y value that it levels off to is this asymptote at -2. So we can say -2. Now, if I'm asking the limit on the left, the limit as x goes to negative infinity, what's happening? So as x goes to negative infinity, where's this curve headed? Well, it's also headed to that asymptote of -2. So same thing, another example. As x approaches infinity, as x goes to the right, where is the y values approaching? They are stopping at pi over 2. So we can say pi over 2. Same thing over here, limit as x approaches negative infinity, we're going all the way to the left, the curve is approaching this negative pi over 2. So limits at asymptotes, or at the end behavior of the graph rather, is relatively easy when you have a picture. Now, how about polynomial functions? If I have a polynomial functions that have a picture, it's obviously easy as well. We could just look at the end behavior. So as x goes to infinity, so as x goes to the right, where's the graph going? Up. As x goes to negative infinity, where's the graph going? Down. So we say negative infinity. This one happens to be an odd function, right? With a leading coefficient that's positive. So this one's odd positive. How about the second one here? This one's odd also. They're going in opposite directions, but this one's odd negative because it's going up and to the left. So what's happening here? As x goes to infinity, as x goes all the way to the right, the y values are going down. Here, as x goes to the left, negative infinity, so now what about the next one? The next one here is an even graph because they're going in the same direction and they're going up. So this one's an even positive graph. So since both ends are going up, as x goes to the left or right, end behavior goes up. So they're both going to infinity. Last one here is also even. They're going in the same direction, but it's negative this time. So this one's even negative. But they're both, whether x goes to the left or the right, they're both going down to negative infinity. So those would be my limits. Now, obviously, again, the graphs are super easy. But what if I gave you a problem like this and I said, find the limit of each polynomial function? And I just gave you this without a graph, and it was a no calculator section. Then you would have to look at the most dominant term, or the highest degree, so such as this one, and this will tell you what type of function this is. So because the 4 is the exponent, and that's even, and because the 3 is positive, we have even positive. So my graph is going to end up. So as x goes to positive infinity, which is the right side, the graph is headed up. So we could say this limit is infinity. The next one, highest power is 5. So x to the 5th, 5 is odd. And the leading coefficient is 1, which is positive. So odd positive is up and to the right. This guy goes down. So as x goes to negative infinity this time, as x goes to the left, the graph is headed down. So we could say negative infinity. And last but not least, as x goes to negative infinity of this function, we're going to look at the highest power, which is this guy as well. So we have 3, which is odd power, but now we have a -1 in front, which means my leading coefficient is negative. So up and to the left and down. So as x approaches negative infinity, the graph is going up. So these are examples of how graphs and knowing end behavior of polynomial functions can help us find limits at horizontal asymptotes. Okay, how about we talk now about limits using dominance? So what does that mean? First, let's analyze the most basic rational function that we could have, 1 over x. Here's the graph. Now on this graph, we know that there is a vertical asymptote right down here at x equals 0. Just helpful to know. So I took the liberty of showing you the table of values as x gets very, very large. So this goes when x is 1, 5, 10, all the way up to x is 1,000. Obviously on here, I only show you up to 4. So what's happening, I want you to make conclusion. As x gets really, really big, what is happening to the y values or the graph itself? 1, 0.2, 0.10, 0.04, 0.02, 0.01, 0.002, 0.001. You should notice the y values are getting really, really, really small, but they're actually approaching a value, and they are approaching 0. So it's safe to say that this limit as x approaches infinity, as x goes all the way to the right, the graph is leveling off to 0, which is another asymptote. So here is our asymptote of the line y equals 0. So that's what's happening. The graph is approaching 0. So it's safe to say that anytime we have a fraction and the number in the bottom is getting really, really big, the limit can approach 0. So the conclusion from this is that the limit as x approaches infinity of 1 over a really, really big number, that limit is going to be 0, no matter what. So this is called dominance, that if the denominator is dominating and it's getting bigger faster than the numerator, we can say that limit would be 0. So now what happens when x gets really, really small? So we're just on the other side of the graph now. Look what's happening to the table. -1, -5, -10, blah, 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 right? These numbers are getting really small. What's happening to the y values? You should look. They're going from -1 to -0.20. They're getting bigger, really, but they're approaching that same value. They're approaching 0. And you can see here, there's another asymptote. It's still that same asymptote. The line y equals 0. So as x gets really, really small, the y values are approaching 0. So we can say, similarly, that same limit, as x approaches negative infinity of 1 over x, the limit is still 0. So that conclusion for this dominance theory is that as x approaches negative infinity this time, it's still 1 over a really negative big number, so a really, really big negative number. I know you could say a really, really small number. That limit is also 0. So again, this dominance theory that I'm trying to talk about is the fact that the bottom is growing bigger or smaller, really, really small, than the numerator, therefore it's 0. So how does this apply to more theories of dominance? So there are 3 conclusions. The first one is that if the denominator grows faster than the numerator, then the limit is 0, which is what I have here. So the denominator is growing faster than the numerator. So what we can do is take the highest power, the highest dominance. So do you agree the highest power here is x squared? And the highest power here is x to the first. So it's called dominance because you're picking the one that has the highest exponent or highest power. So obviously I have the answer here. As x approaches infinity, we can see that the graph is going to 0, and we can see this graph is going to 0. So let's prove it algebraically. So we can simplify this f of x into just these 2 terms. So I want to take the limit as x approaches infinity of x over x squared. And we can simplify that. So lim as x approaches infinity of 1 over x, right? I just divided out the powers. Now, what did we say before? If x is getting really, really big, as it goes to infinity, this limit would be 0. So same thing on this side. We can say the lim as x approaches negative infinity of x over x squared can still simplify to 1 over x. That limit is also 0. Okay. The second theory of dominance is that if the numerator grows faster than the denominator, notice here we have a negative 3x squared on the top and we have a 3x on the bottom. So the top is growing faster because it's squared. Squared functions grow faster than linear functions, right? So we can just simplify our function into those 2. And we say this limit is going to be positive or negative infinity. So let's prove it. So the limit as x approaches infinity of negative 3x squared over 3x. Well, I can simplify this to the 3's will cancel. The x squareds will have a leftover x on top. So lim as x approaches infinity of just negative x. So we're going to do direct substitution. What happens if we plug in a really, really, really big number for x? Say it's -1 million, a million, and then negative is just -1 million, so negative infinity. Okay, next, Limit as x approaches negative infinity, we can again simplify this to negative x as well, but this time we're going to do direct substitution again, but we're going to plug in negative a million. So negative a million is going to be positive, or positive infinity. So that proves it from my graph, right? The limit from the right, or positive infinity, this guy, goes down to negative. Limit from the left, negative infinity, the graph goes up. Okay? And then the last one is this ratio of the coefficients. So what we could do when we have that is when the numerator and denominator grow at the same pace, meaning they have the same power. So we're going to take just the top, the 3x squared, and the x squared minus 4. So we're going to take the lim as x approaches infinity of 3x squared over x squared. Notice the x squareds can cancel. So we have the lim as x approaches infinity of 3. And the limit of a constant is itself. So that proves it. Limit as x goes to infinity, as x goes to the right, the graph goes to 3. That's that y value of 3. Same thing on the bottom. We can do the lim as x approaches negative infinity of 3x squared over x squared. Again, the x squareds will cancel. So the limit as x approaches negative infinity of 3, limit of a constant, is also 3. So look, limit from the left, negative infinity, is also 3. So these are our 3 rules. If the numerator is growing faster than the denominator, you can just look at this and just say, okay, the limit is going to be 0. Here you have the numerator growing faster than the denominator. So here my limit is going to be plus or minus infinity. You have to do some work to figure out which one. And here, if the denominators are the same, it's simply the ratio of the coefficients. And we got 3. Isn't that the ratio? Ratio meaning divide or fraction. So fraction of the coefficients. So 3 divided by 1 is 3. That is your ratio of your coefficients. Okay, so you have 6 examples here. I'd actually like you guys to try these for homework. And I will start class by going over those tomorrow. These 6, and we'll start class there. All right? Have a good night. Now, I know there's a 3rd page here, but I think we're going to end the video here, and I'm going to do these in class tomorrow. So don't stress about getting up to this page, but I do want you to do